Calculus 12, Chapter 5.5, we're going to be looking at the trapezoidal rule. And it's a more efficient RAM, and it's always better to use RAMs that have a better estimate with smaller ends, because this reduces the numerical errors and computes quicker. But in all honesty, the MRAM has a better estimate than the trapezoidal rule. So let's take a look at it. The trapezoidal rule, to approximate the definite integral, we use t equals h over 2. The first value plus twice the second value plus twice the third value, and so on, plus twice the second last value, plus just the last value. Okay, so we double up every value except the first and last. Where the closed interval a to b is partitioned in n subintervals of equal length, h is equal to b minus a over n. Okay, h is not great because we use h for height, but here we say the width is h. If you've already calculated LRAM and RRAM, we can have t equals LRAM n plus RRAM n over 2. N is the number of partitions. So where LRAM n and RRAM n are the Riemann sums using left and right endpoints respectively for the function f for the partition. Notice this is the same formula that we used in the RAM list calculation. Here's an example, number 2. Do the definite integral from 0 to 2 of x squared dx, where n equals 4. So we calculate the width of the partition, h equals 2 minus 0 over 4, and that's a half. If we have 4 partitions, we need n plus 1, so 5 data points, equally spaced. So t equals 1/2 times h, which is 2, and the first data point, plus 2 times the second data point, plus 2 times the third data point, plus 2 times the fourth data point, plus just the last data point. So we have 1/4, and let's use fourths for everything. 0 plus 2 over 4 plus 8 over 4 plus 18 over 4 plus 16 over 4. This gives us 1/4 of 44 over 4. So this is just 11 over 4. Part B, let's take a look at the second derivative to determine the concavity. So the first derivative is just 2x. The second derivative is 2. This implies that it's concave up. Since it's concave up, it's an overestimate. Therefore, overestimate. Okay, let's calculate the exact definite integral. So we have x cubed over 3, and we're integrating from 0 to 2. So we have 8 over 3 minus 0. That's 8 over 3. Okay, let's have a common denominator between this and this so we can do a comparison. We need to multiply this by 4 over 4. So this is 32 over 12. We need to multiply this by 3 over 3. And we get 33 over 12. So we can see that this is an overestimate of the actual value. Why is that the case? Well, let's look at this. Okay, so if we have a curve like this, and we're doing trapezoid, the trapezoid is an overestimate when it's concave up. Now, this is predicated that we're looking at positive functions. If it's negative functions, it's going to be the other way around. Okay, let's look at this. So here, if we do a trapezoid on a curve that's concave down, this is going to be an underestimate. And this is an overestimate. Okay, because the trapezoid sits below the curve. Can we get a better approximation? And of course, that's a loaded question. Yes, we can. Simpsons Rule, an even better approximation for curves. Why? Because it uses parabolas to calculate the areas. Okay, so Simpsons is h over 3. We have the first data point plus 4 times the second data point plus 2 times the third data point plus 4 times the fourth data point, and it's going to alternate between 4 and 2, plus 2 times the third last data point, plus 4 times the second last data point, plus just the last data point. Okay, where a to b is a closed interval and is partitioned into an even number of n subintervals of equal length, h is equal to b minus a over n. Okay, let's take a look at this. We're alternating between 4 and 2. We have to end up with a 4.
This is important.
So that means there's an odd number of data points here. Adding 2 more data points makes it odd still. And remember, the number of partitions is 1 less than the number of data points. So we have an even number of partitions. If we have an odd number of partitions, we would end up with a 2 before adding the last value. And we can't have that. Okay, so let's look at using this. Approximate the definite integral from 1 to 2 of 1 over x dx using LRAM, MRAM, RRAM, trapezoidal, and Simpsons with n equals to 8. Then calculate the definite integral. Okay, I'm going to save some time, assuming that you know how to use LRAM, MRAM, and RRAM. So, trapezoidal, we just take LRAM, add RRAM, and divide it by 2, and we get this value. Let's calculate h. h equals b minus a over n. We're just repeating this so it's easier to memorize. So our width is 1 over 8. So S equals h over 3 f of 8 over 8. And I'm not putting in 1 because it's convenient to leave it as in terms of 8s, because it makes it easier to continue. You'll see why. 4 times f of 9 over 8 plus 2 times f of 10 over 8, and we're not simplifying that, plus 4 times f of 11 over 8 plus 2 times f of 12 over 8 plus 4 times f of 13 over 8 plus 2 times f of 14 over 8 plus 4 times f of 15 over 8 and plus f of 16 over 8. Okay, so this is 1 over 3 times 8. And remember, our function is 1 over x. So all we're doing is taking the reciprocal of these values. So we have 8 over 8 plus 4 times 8 over 9 plus 2 times 8 over 10 plus 4 times 8 over 11 plus 2 times 8 over 12 plus 4 times 8 over 13 plus 2 times 8 over 14 plus 4 times 8 over 15 plus 8 over 16. And I would do that on the calculator. We get 1 over 24 times 16.63570874. And I'm only carrying that many digits because that's how many digits we have up there. And we perform this division. We get 0.69315453. Let's do the integral. Integral from 1 to 2 of 1 over x dx equals, and you can just do this on the calculator with a numerical solution, 0.69314718, and that equals I, and that's. And if you remember the antiderivative of 1 over x, that is ln x. So we have ln 2 minus ln 1, which is just ln 2, and that's our exact value. Okay, let's do some error calculations to see which approximation is the best. Okay, so we take our LRAM minus I, multiply by 100, and divide that by I. So you always do the difference of the estimates and divide it by the actual value or the exact value and multiply that by 100. And we get 4.648. I will let you do those calculations yourself and you can compare to what I have. 4.369%. So those are not great estimates. So MRAM gives us 0.0713%. That's pretty good. TRAM, trapezoidal, 1394. So you can see it's not quite as good as MRAM. Now, Simpsons Rule, 0.0011%. Okay, that is fairly accurate. That is 1,000 times better, more than 1,000 times better than these two estimates. It's still 70 times better than MRAM. So you can see we get very accurate results with n only equal to 8. Okay, on a table, we can use trapezoidal or Simpsons rule just as easily as on a function. Okay, so we calculate the width, take two data points that are consecutive, and take the difference, and that's 0.5, so half. Okay, so Simpsons rule, we have to have an odd number of data points, so we have an even number of partitions. Let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 data points, so we have 10 partitions. So we're okay to go ahead with the calculation. And I've copied this down for you so you don't have to copy it. S equals H over 3, first data point, 4 times the second data point, 2 times the third data point, 4 times the fourth data point, and so on, and adding up the last data point. Okay, and we just substitute the values in. And we plug it in on the calculator, we get 1/6, and the sum is 268.41. And that equals 44.735 meters. Don't forget your units. Okay, let's take a look at this on a calculator. We got to go to Stat to enter our list. So 0, 4.67, 7.34, 8.86, 9.73, 10.22, 10.51, 10.67, 10.76, 10.81, and repeat the last one, 10.81. Okay, we're going to execute RAM-L, and the width is 0.5. LRAM, not terribly accurate. MRAM, pretty close. RRAM, not so close. TRAM, again, it's going to produce the same value as MRAM. And SRAM, 44.735. And that completes this lesson.